Good everyone, my name is Graphics. If you look at the front of your screen, you will see a question, and the question says, determine the heat transfer and its direction from a system in which a perfect gas having a molecular weight of 28 is compressed from 101.3 kilopascal at 50 degrees Celsius to pressure of 430 kilopascal following the law PV to the power of 1.3 equals to constant. Take the specific heat at constant volume of gas as 0.45 kilojoule per kilogram Kelvin. Now, what you see here, kilojoule per kilogram Kelvin, is telling you that any temperature you have that is not in Kelvin, convert it to Kelvin. So the first thing you do here is for you to write out your data given. So the first data we have here is for the molecular weight, and it's giving us M sub W. You can just say M, capital letter M, which is giving us 28 kilogram per kilomole. Now we have what they call the pressure, because it said it is compressed from. From means it was somewhere, that is the initial point. Are you with me now? To means destination. From means the origin. To means what? Destination. So in this case here now, when you hear the word from, it means initial. And when you hear the word to, it means final. So we have two states here. We have the initial state and the final state, meaning state 1 to what? 2. Are you with me now? We're moving from state 1 to 2. That is a process. So when you see me using sub 1, I mean initial state. If I'm using sub 2, we're talking about final state. So sub, I'm talking about subscript. Are you with me? So we have another data here, which is the initial pressure. We use P sub 1, which is equals to 101.3 kilopascal. We know the K there is kilo, and kilo means 1000, and 1000 means 10 to the power 3, right? So when you multiply 101.3 times 1000, you'll be having 101,300 pascal. And we know pascal is essentially saying Newton per meter square. So move to the next one, which is the initial temperature, which is giving us T sub 1, and that is 50 degrees Celsius. Remember, we convert to what? Kelvin, by adding 273. So 273 plus 50 will give us 2323 Kelvin. Now we'll go to the next one. It says to a pressure, which is the final pressure, of 430 kilopascal. So we use P sub 2, and 430 kilo means 430 times 1000, and that is 430,000 pascal, or we say Newton per meter square. So we'll move forward. The relation given here, we call it Polytropic process, given as PV raised to power 1.3 equals to C, constant, right? And we're given specific heats at constant volume, C sub V equals to what? 0.45 kilojoule per kilogram Kelvin. So if I remove the kilo, which is 1000, I'll multiply it by that 0.45, and that will give us 450 joule per kilogram Kelvin. And we're told to find Q, which is the heat transfer, Q. So that's what we're looking for. So the assumption in this system here is that the gas that we use is a perfect gas, and the process is a polytropic process. The expansion is what? Is a polytropic process. So we'll move forward. Now, like I always tell you, is that in cases like this, especially when you are looking for a direction that you don't know where to start from, we are told to look for what? The heat transfer. So what I would just advise you is, what is the formula for the heat transfer in this kind of process where you have your temperature, pressure, molecular weight, and we have the specific volume. So what is your what? Your heat transfer. So the formula for the heat transfer in this kind of situation here is given as Q equals to what? The specific ratio minus N all over specific ratio minus 1, all multiplied by what? The work. So it means that for me to get my heat transfer, I need to know my specific ratio, I need to know my polytropic index N, and I need to know my work. That will give me my heat transfer. Can you see the direction here? So this will guide you. So the first thing and foremost, what we'll look for, I will term that my equation 1, right? So first thing we look for is my specific ratio. So let's look for specific ratio. Specific ratio, right, is given with the symbol like you can see gamma is equals to the constant pressure all over what? Constant volume, right? So I will term this my equation 2. Now if you look at this closely, I don't really know my constant pressure, but I know my constant volume as given in the parameters there. Constant pressure is equals to constant volume plus gas constant, right? So we know the constant volume, but we don't know the gas constant. So I'll term this my equation what? Equation 3 here. So if I should know my gas constant, I will just put it in here to get my what? My constant pressure. So what's my gas constant? My gas constant R, recall my R here is equals to what? My universal gas constant all over what? The molecular weight. So if I input my value, I'll be having this to be my universal gas constant is given as what? 8314 in terms of what? Joules per kilogram Kelvin. Is that taken? But in kilojoule per kilogram Kelvin is given as 0.8314. But we are working with just joules. So we have 8314 all over the molecular weight is given as what? 28. So when you divide 8314 over 28, my gas constant will now give me 297 joule per kilogram Kelvin, or in terms of kilojoule, we have dividing by 1000, we have 0.297 kilojoule per kilogram Kelvin. So we've gotten our R. So we'll now put it into the equation above, right? So put in equation above, that is equation 3. Above, we'll have Cp equals to Cv plus R. That's the equation there. So Cp will now give us Cv is 450 plus the R we got here is 297. So my Cp will now give us 746.9 joule per watt kilogram Kelvin, which is also in terms of kilojoule per kilogram Kelvin. You divide by 1000 and we have 0.746 kilojoule per kilogram Kelvin, approximately 0.75. So we've gotten that. So now you put it into our specific ratio that says from the equation above that says specific ratio is equals to Cp all over what? Cv. So what is our Cp now? 746.9 all over 450 equals to 1.66. So that's our specific what? Ratio. So we've gotten that now, right? So now remember one of the parameters we get, which is what? The work. So for the work here, we know that our work now will give us R T1 minus T2 all over N minus 1. So my W will now give me, so from here, we have our R, we have our N, we have our T1, but we don't have what? Our T2. So I'll term this my equation what? Equation 5. So I'm looking for what? My T2. So in looking at my T2, we know very well that my polytropic process in terms of temperature and pressure, right? We're looking for T2 now. In terms of temperature and pressure, will be giving us P to the power of what? N minus 1 times T to the power of N is equals to C. So since we have two different processes, two different states, 1 and 2, so we're having P sub 1 raised power N minus 1 times T sub 1 raised power N is equals to P sub 2 times N raised power N minus 1 times T sub 2 raised power what? N. Now when you make your T2 the subject of the formula, you'll be having, first of all, collect your like terms, bring the P together and the T together. So we'll be having P sub 1 to the power of N minus 1 all over P sub 2 raised to the power what? N minus 1 is equals to T sub 2 raised to the power N over T1 raised to the power what? N. So if you apply your indices, since they have the same power, we're having P1 over P2 raised to the power what? N minus 1 is equals to T2 over T1 raised to the power what? N. Now remember, if the power you see on top of a T2 over T1 has a denominator of 1 because you can't see. So because N over 1 is N. So if it's coming to the other side, it will what? It will interchange. So we'll now be having P1 over P2 raised to the power 1 minus N times 1 over N. And 1 over N times n minus 1 will give you n minus 1 over n. So equals to T2 over T1. So if I cross multiply, my T2 will now give me T1 times P1 over P2 raised to power what? N minus 1. So that is how we calculate for T2. So T2 will now be, what's the value for T1? 323, open bracket, the value for P2, 430,000, value of P1, 101,300, raised to the power of what? N is 1.3 minus 1 all over n, which is 1.3. So 1.3 minus 1 is 0.3 all over what? 1.3. And when you divide 0.3 over 1.3, you have 0.231. And when you divide 430,000 over 101,300, you'll be having what? 4.25. So 4.25 raised to power 0.231 will give us what? 1.397. If you multiply it by 323, you'll be having 451 Kelvin. So that's my final temperature T2. So now we can now input it in our equation 5. So in doing that, my work now will now be giving me the gas constant R, which is given as 297, multiplied by my T1, which is given as 323, minus T2, which is given as 451, all over my n is 1.3 all over minus 1. So in the long run, when you subtract 450 from 323, you'll be having minus 128 divided by 0.3, and that's going to give us minus 426.67. Right? Now if you now multiply it by 297, you'll be having minus 126,720 joule per kilogram. So in terms of kilojoule, you divide by 1000, so you'll be having 126.7 kilojoule per kilogram. So we've gotten my work here. So I'll now input it to my equation 1 at the beginning. So we'll say that the heat transfer will now give me the specific ratio minus the polytropic index all over specific ratio minus 1 multiplied by W. That is equation 1, right? So you put your value. Specific ratio is given as 1.66 minus 1.33 all over 1.66 minus 1, all multiplied by what? Minus 126,720, right? So when you now subtract 1.66 minus 1.33, you have 0.33. And when you subtract 1.66 minus 1, you have 0.66, right? So 0.33 divided by 0.66 is 0.5. Then multiply by minus 126,720, and that will give us minus 63,360 joules. And if you divide by 1000, you have minus 3.4 kilojoule. So this is the heat transfer here in the polytropic process. So in this case, the negative signifies that, you see, when there's work done on the system, right, it is always negative. Because when you are doing work, it's always negative. But when heat is supplied to a system, it's positive. When it is rejected, it's negative. So the direction here is negative, signify that for negative heat, we say that what? The heat is rejected by the system. And for the negative work, we say work is done on the system. So this is what we have here. So if you found this video helpful, please don't forget to like, subscribe, and also share the video. Thanks for watching.